Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 Chemistry students. Welcome back. I'm Alan, still with you in chemistry. We are still on Unit 11, which is about solubility and the solubility product constant for sparingly soluble salts. We are heading in for Lesson 2, factors affecting solubility of a sparingly soluble salt. Welcome. I hope you're safe and still healthy. I'm glad to meet you once again. So, before we look closely on Lesson 2 content, I want to check up on the answers you got on the exercise we did, the example we did in Lesson 1. That is the answer you're supposed to have got. Please check up with your calculations if that is the answer. So we had done that number together, but I left you without finding the answer, but that is the answer. Take note of it. So let's now go to Lesson 2, factors affecting solubility of a sparingly soluble salt. We're going to look in details mostly about 4 factors. One is the temperature. At the start of Lesson 1, we talked about how temperature can affect solubility. So in this case, we shall go through it. Then complex ion formation, precipitation of one of the ions in solution from a sparingly soluble salt, then common ion effect. Those are the 4 factors we are to look at and with one objective, summarizing all the 4 factors. The objective is you should be able to describe and explain how each of those 4 factors outlined as you see them, how they affect solubility, what happens if you alter those factors. So let's directly go to factor 1, which is temperature. The effect in here depends on whether the dissolution is endothermic and exothermic. And when we talk of endothermic, from your thermochemistry understanding, so the endothermic reaction occur after they've gained heat from the surrounding. So in endothermic, we have heat being absorbed. And as such, the overall energy change is normally positive value. On contrary, the exothermic reactions, for them, they release heat to the surrounding. So they are indicated by a negative value. In other words, the products are normally having a lower energy compared to the reactants due to the loss of energy to the surrounding. So those are the minor things you need to have in mind to know that this reaction is endothermic and this reaction is exothermic, or it gives out heat. Let's look at a few examples. We have an example of an endothermic reaction, that is silver chloride dissolving, forming silver ions and the chloride ions. By the look of that positive value, the enthalpy of solution, looking at its positive value, that directly tells you that that is an endothermic reaction. So what happens when we alter the temperature for such a kind of a reaction? Of course, being endothermic, it will be favored by high temperature. And so increase in temperature directly increases its solubility. A prominent example in here is lead 2 chloride. It's actually very, very endothermic. When you heat the lead 2 chloride precipitate, it quickly dissolves, forming a clear solution. But cool it, it reappears. And that is one of the characteristics we base on when we are identifying the chloride or the lead ions in solution, that endothermic change. So let's look at the exothermic. An example is lithium chloride. You see the value. It has a negative value, negative 37. That indicates this reaction is exothermic. And by the principles of the exothermic reaction, the more negative, the more it is likely to occur. So with lithium chloride, for instance, it is more soluble with lower temperature because it gives out heat. So it is favored by low temperature. A point to note in here is if the enthalpy change of dissolution or the solution is more negative, then that salt can dissolve very, very fast at low temperature. So it is considered to be more soluble. But for those which require heat, that is for endothermic, their solubility increases with temperature. So that is it with the temperature. Let's look at complex ion formation. This one increases solubility because the ions complex up with the other components you've added. Let's look at the silver chloride still. It is more soluble in ammonia compared to water. These are the illustration. Check at it. This is silver chloride in water. It forms the white precipitate. But add ammonia solution, it dissolves, forming a clear solution. You see the amount has increased in the addition of ammonia. So what is the reason behind that? As we said, the salt is in equilibrium with its ions in solution. So add ammonia, the ammonia will form a complex with silver, and that is what we call diamine silver 2 ions, or the complex of silver. So the presence of ammonia molecules complexing up with silver reduces the amount of silver at equilibrium. So for the Ksp to be regained, more of the silver chloride salt will have to ionize, forming silver ions and chloride ions. In the process, more of the salt is ionizing, is dissolving. And that is how the complex formation increases solubility. It disorients the Ksp. And so, since it is a constant, it has to be regenerated, or it has to be stabilized. And in the process, more of the solute or the salt dissolves. Let's look at another example. Lead 2 chloride is also more soluble in concentrated hydrochloric acid than water or than dilute. Reason, it complexes up with the chloride from the concentrated hydrochloric acid to form the complex tetrachloroprambate ion, this one. So in the process, lead 2 chloride will continuously be dissolving. So that is for the complex. The third factor we have to look at is precipitation of one of the ions at equilibrium. Precipitation, formation of another salt, which is totally different from what has been dissolved. That is what we mean by precipitation in here. Example, still using silver chloride, I want you to understand how these factors affect silver chloride, for instance. Then you transfer the knowledge to another sparingly soluble salt. Silver chloride, it's more soluble in lead 2 nitrate than in pure water. Simple understanding. So in pure water, it exists like this. You see the ions. But when you bring in lead 2 nitrate, the lead 2 ions in solution pick up the chloride to precipitate lead 2 chloride. In the process, more silver chloride will ionize to bring in more chloride since they are being removed. So what is happening in here is like you have your jerrycan, a 5-liter jerrycan. You're adding water, but one at the bottom, the jerrycan is empty. As you're adding, it has a hole. As you're adding water, more water continuously flows out. So you will continuously add as it flows out. Continuously add as it flows out. This is what is happening with the precipitation. Again, using this example. So what is happening is the lead will continuously remove the chloride. So the silver chloride as a salt will continuously dissolve to bring in more chloride ions that are being removed by lead. And in that case, it becomes more soluble in lead 2 nitrate. Same principle with barium sulfate, more soluble in lead 2 nitrate than in water, because lead precipitates the sulfate as lead 2 sulfate. So the barium sulfate has to continuously dissolve to bring the sulfate ions. So the last factor we have to look at is the common ion effect. Common ion. The crucial word is this word, common, indicating the solution we are adding in a saturated solution of a sparingly soluble salt has the ion which is similar to the ones we are having in the solution. So what happens is this common ion reduces the solubility. Question is how? Again, with our silver chloride. Let's take a close look and understand what happens. You have your silver chloride, which has partially dissolved, giving silver ions and the chloride ions, indicating it has reached an equilibrium. It has stabilized with its KSP. Add something like sodium chloride solution, which brings in the chloride ions. So in this case, the chloride ion is a common ion for both silver chloride and sodium chloride. When you add in the sodium chloride, the introduced chloride ions will increase the concentration of chloride ions in this saturated solution. So the KSP will be disrupted. To regain the KSP, then the chloride ions must combine with the silver ions, forming undissolved silver chloride. So you see, now the reaction goes backward. Chloride, which has increased in amount, combines with the silver ions to form the silver chloride salt. So the solubility reduces because the amount of the chloride from silver chloride have reduced. What is in the solution are the chlorides from sodium chloride. So a point to note in this common ion effect is to reduce the solubility, you need to add in a salt which is more soluble than that sparingly soluble salt. Example is this sodium chloride is more soluble than silver chloride. So the solubility will terribly reduce. So those are the 4 factors: the temperature, the complex ion formation, precipitation of one of the ions at equilibrium, and the addition of a salt which is having ion similar to the one you're having in the sparingly soluble salt. And you've seen how they really affect. You should be able to describe and explain those factors in details. So let's practice a few questions before I leave you with the exercise. I will call this Unit 11, Exercise 1. We hadn't done the exercise. So this is the exercise. I'm going to go with you this number 1. I will leave number 2 for you. You see, I've even given you the answers for you to quickly correct yourself. But let's first go through number 1. Then we can see what comes next. So we look at a few examples. Exercise 1. What does it say? We are having lead sulfate. You need to be knowing how to write the equations, because sometimes they will not give you the equation. But if you're lucky and they give you the equation, advantage. But you need to be knowing how to write the equations. This is lead sulfate, was shaken with water to make a liter of solution. So add amount of water in form of the aqueous. It will dissolve, since it is sparingly soluble, to lead 2 ions plus the sulfate ions. The ratio here, it is 1 to 1 to 1, something you will need to apply. So what is the question wanting us to do? A is to get the KSP, concentration of lead 2 ions raised to the power of 1, since the mole ratio is 1, and the concentration of the sulfate ions. This is our KSP, which will be mole squared per decimeter 6 as the units. You understand where that one is coming from. Next, we are to determine the specific mass of lead 2 sulfate that dissolved. They want the specific mass. In this case, they want solubility in grams per liter. That's what they are asking us, the specific mass that has dissolved. So what do we have? We have KSP, and we have the atomic. So we are going to first get the solubility in terms of moles per liter, then we convert it. Let's assume, let's say, solubility of lead sulfate in moles per liter be, let me call it S. You can use any number you want. So in this case, we shall use our KSP, which is KSP. I will substitute. Remember the solubility. In this case, it is in terms of the concentration of these ions in solution. So I've called it S. What does that imply? It's the concentration of lead 2 ions, depending on how you want, which is equal to the concentration of sulfate ions, since the ratio is 1 to 1, and this is S. These, the amounts in solution are the ones which give us solubility, and we've called it S. Let's substitute it in our KSP, which would be S times S. And this KSP is been given to us as 1.6 times 10 power negative 8 is equal to S squared, indicating S will be the root of 1.6 exponent negative 8. So what is that? That is 1.6 exponent neg 8 root 1.264 times 10 power negative 4 mole per decimeter cubed. So this is our solubility, which we termed as S. Now, this is in moles per decimeter cubed, but the question wants us to determine solubility in grams per liter, the mass that dissolved. So we must convert this from moles per liter to grams per liter. So to change it to grams, we need the molecular mass of this case lead sulfate. How do we get the molecular mass? Lead is 207, we've been given to us. The sulfur is 32, oxygen is 16, but there are 4 atoms. What do we get? Using your calculator. Go with me. Let me see who will get the answer first. It's the 4. This is 303 grams per mole. So, how do we get the solubility in grams per mole? Of course, in this case, it would be the concentration. Okay, let me call it this way. So, solubility in grams per liter will be this. We multiply it by the molecular mass, 1.264 exponent -4. This is in moles per decimeter cubed. Then we multiply it by 3. We need to mass. We multiply it by 303 grams per mole. You will get 0.038 gram per liter. The per mole here, gram over mole, the mole will go with the mole up here. We remain with the gram and the decimeter, which is per liter. So that is the amount that dissolved in a liter for lead sulfate. Next, determine the percentage of lead 2 sulfate that dissolved. The percentage, which we need the original mass over the original mass, which has been given to us as 5 times 100. What do you get? .038. You'll get 0.76%. So this is the percentage, and this is the specific mass that dissolved. So that is it, and that is how you can easily interpret a question of solubility, then you calculate it. As I said, I'm leaving for you that question 2 for you to try and go through it. So, in the same case, I'm giving you a homework. This is read ahead of teachers. This is homework I'm leaving for you to go and read first, then you try it. We shall do it in our lesson 3. It's about calculations involving common ion effect on solubility. It is kind of different from what we've just calculated, but it has one aspect in common. You need to first calculate the solubility. In this case, we have that question. It is clear. I will only highlight and see and bring in where we talk of common ion effect. And that is question 1, part B and C. Look at part B. It is talking about a saturated solution of barium sulfate has that amount. That is gram per liter, which we call the solubility in grams per liter. Then they added barium chloride. Remember, barium chloride is bringing in the barium ions in solution. We're already having barium sulfate, barium and the sulfate ions, but you're adding barium chloride, so you're bringing in the barium ions. So that is what I want you to go read up and find out the answers. We're going to start from there next time. Thank you for your attention, and thank you for being part of the lesson. Please keep safe, follow the Ministry of Health regulations. I want to see you next time.